I'm going to use this example problem to walk us through the steps to solve a basic kinematics problem. We have a uniformly accelerated motion of a driver. In this case, they're slowing down. We're going to walk through how to set up a problem. At first glance, things might look a little more complicated than they can be, but if we take this process, I think it'll simplify everything for us. With any problem, let's start with drawing a picture. Really, we've got to get an idea what's going on. All of these problems that we're going to be doing are one-dimensional problems, so we could picture every object as existing on a number line. All right, so I'm going to draw my number line. In this case, it's in the x direction. We might see things vertically, which would be in the y direction. Let's define direction. So I'm going to put a plus and an arrow to the right to indicate that anything moving along this line is moving in the positive direction. And so now we're going to put the object on here. Now, they don't tell us a location the object is starting at, so let's just put the car on the left side. And let's define that as a location of 0 meters. So now we've defined where they're located, and that car later is going to be over here on my screen. And so it's on a number line. It's going to be some positive position. Let's look at what else we know. Well, this car is initially moving, and so we can represent that motion, a velocity, with a vector arrow. So I have this car moving to the right. That's its velocity. If I want, I can label it with the value. But most important is the arrow and that it's pointing to the right, which is going to indicate positive. Now, this car is slowing down. We see that it's going 15 meters per second later. So that will also be an arrow for this later position. But since it's slower, I'm going to draw a shorter arrow because I expect that value to be less. And I'm going to write 15 meters per second air. They tell us of a time. We know the time is 4 seconds. I can write that in here. But this car is also slowing down. It's helpful to draw the acceleration vector on your page. Now, which way does the acceleration point? Well, it depends on what's happening to this car. This car is changing its velocity. It's slowing down. When we talk about momentum, there's an impulse on this car. It's actually the road, the friction that's going to be slowing it down. Well, which way does it point? Well, to slow a car down that's moving to the right, that acceleration will have to point to the left. So I'm going to write A here and with an arrow to the left. And that's a really helpful reminder that I'm expecting a negative value for the acceleration. So now let's look at this table. So I'm going to take this picture and I'm going to translate some of these values in here. I'm going to put x final here and write in our table what we have. We have these equations up here. These are our kinematic equations. And so we have variables that apply to the motion of this object. And I'm just going to organize what I have in the problem here in this table. They want to know how far the car's traveling. Well, if it starts at a position of 0, I'm going to write the 0 meters here. How far it goes would be whatever that final position is. I'm going to put a little star there. They don't tell us the acceleration. I do expect a negative answer, though, for my acceleration. So it might be helpful to put a negative there, but we don't know that value. They tell us the time it takes is 4 seconds. Our initial velocity is to the right. I'm going to put a positive there of 27 meters per second, even though if I just write 27, it's assumed positive. Get in the habit of writing the sign with any velocities. Later, the car is still moving to the right, but we have 15 meters per second of velocity. So that's my table filled, and I'm missing 2 pieces of that table, and I'm trying to find the final position. So to find the final position, I'm going to look at my equation. I only have the final position in one spot. It's right here. So now that I have these variables in here, I'm going to put a dot in my equations over all the things I have. Well, I don't have the acceleration. I'm going to put a question mark there. I'm going to put it over here as well. But I'm going to put a dot over the time, the initial velocity, and the initial position. I know both velocities, and I know the time. So as I go through here, I'm now asking myself, well, is there one of these equations that I could find a missing piece? Well, I want x final. However, I'm missing A, the acceleration. However, in this second equation, I have everything except for the acceleration. So now I can use that second equation and solve for A. So I'm going to take equation number 2, which says that the final velocity of the object is its acceleration times its time plus its initial velocity. And now I can substitute the values I have. I have 27 meters per second. I can write the units in there. Most importantly, if I look in my table, I have seconds and meters, so I should be good to go. Everything's going to cancel out, so I'm going to simplify and just leave it as 27. I don't know A. My time is 4, and my initial velocity is 15. And now we have an algebra problem. I'm going to solve this algebraically. I can isolate the A value. I'm going to subtract 15 from both sides, and I get 12 is equal to A times 4, which I can then divide by 4, and I get 3. Now, I got a positive value, all right, which means that doesn't match what I'm expecting. So because I've organized my work, I might be able to catch a mistake right here. Does anybody see that mistake? Well, now that I'm looking, I think I switched my velocities. My final velocity is actually 15. So I'm going to erase my work here. My final velocity is 15, and my initial was 27. And when I do the algebra now, that goes away, and I get negative 12 as my change in velocity. And when I divide both sides by 4, I now get that my acceleration is negative 3 meters per second squared. And so, as expected, I get a negative 3 meters per second squared as my acceleration. It's negative, which is what I expect. My arrow points left. So again, by drawing the arrow left, I was able to catch a mistake I made, which was simply plugging in my velocities in the wrong spot. Well, now that we have A, I can check that A off in both spots, and now I can find that final position. So my final position, I can plug in the values in that first equation. I'm going to put negative 3 for A. My time is still 4 seconds. I'm going to square that. My initial velocity was 27. My time is 4. And my initial position, I decided to call that 0, and I can solve and find what that final position will be. If I pull my calculator out, my first term is going to be 0.5 times a negative 3 times 4 squared, which should be 16. I should get a negative value here when I evaluate. In fact, I get negative 24, and that would be in meters, plus 27 times 4. That's the distance I would be traveling over that 4 seconds if I didn't change my velocity. That's 108. And so my final position would be 84 meters. So I can write that in here. And because I started with 0 meters as my starting position, and I finish at 84, well then the distance, how far I travel, would be 84 meters. So I've worked my way through and got to an answer. I have one piece here I want to finish with here. I do want to graph this motion. Sometimes it can be helpful to do it at the front end. It could also work at the back end. I'm going to walk you through the process of graphing here. I'm going to start with the position time graph. We know the position of this object when it starts. We defined it to be 0. And later, this car is located away from 0. The farthest it's going to be, let's put it up here. Let's call that a height of 84 meters, or a distance of 84. But how does it get there, right? If it was at constant velocity, we'd expect a constant slope. But we know that it's not constant velocity. In fact, we know the velocity is changing. It starts fast and finishes slower. Well, velocity on a position time graph is the slope. We have a steep positive velocity. So I'm going to plot a really steep line here. And later we have a less steep positive velocity. So I'm going to still have it positive, but now it's less steep. And when I blend those together, I start to see this curved parabola shape where the slope is decreasing, but is always positive. This car is always moving in the positive direction, but is slowing down. Now, what if I plot those values on the velocity time graph? Well, a very steep positive velocity would be a data point here. And later, it's still a positive velocity, not 0, but positive in here. And it's decreasing at a constant rate. And so I should see a line through here. And the slope of that line should be negative. And in fact, the slope of that line should be the acceleration, which would be negative 3. And remember, this is meters per second, this is seconds. So the units would be meters per second, which is meters per second squared. All right? And so anytime we're dealing with uniformly accelerated motion, that's the same as saying constant acceleration. We should see a linear velocity time because the slope of velocity time is acceleration. So here's a good little problem, kind of walking through the steps of how to organize with a picture, identifying the variables, using those two equations, identifying what's the next step we can do. In this case, you had to find the acceleration before you could find that final position. But each of those steps, if you're careful, aren't incredibly difficult. And this whole process starts working its way through and we can get to an answer that makes sense. So use this strategy moving forward when you're setting up any kind of kinematic problems. And as long as you're careful, I think you can navigate yourself to a solution.